Welcome back everyone. In this video we will continue our TinyUSB journey, and this time we are going to build our very own mass storage device using the Raspberry Pi Pico. So far we have explored how to create and validate a FAT12 file system. Now it's time to take the next big step, integrating that file system with TinyUSB so that our Pico behaves like a real USB flash drive. If you haven't seen the earlier videos, make sure to check them out first. I have covered the basic of FAT12 file system, boot sector and root directories there. We will be skipping those parts today to focus entirely on USB integration. So what will be our objective? First, we will understand how mass storage devices work with respect to TinyUSB. We will understand how TinyUSB handles storage operations and build a mass storage device using it in our Raspberry Pi Pico. And finally, we will integrate our FAT12 file system with it. By the end, our Pico will appear as a USB drive when plugged to a computer. Now let's understand what a mass storage class device is. It's a set of communication protocol that makes a USB device accessible to the host computer and enables files transfer between the host and the USB device. This standard is defined by the USB Implementer Forum or USB-IF. To a host, the USB device acts like an external hard drive. Some common protocol used in mass storage device class are bulk-only transport. This handles how command and data are transferred over the USB. SCSI command set defines what commands are used to perform read, write or inquiry operation on the storage. Together, they let the TinyUSB running in Pico talk to the host computer just like a real USB drive. Now let's see how TinyUSB helps us. TinyUSB takes care of the low-level USB communications. It handles how data is sent, received and managed between the host and the device. For our application firmware, TinyUSB provides several different callback functions that we have to use. First is device identification status callbacks. Under this, we have inquiry callback function. Using this, we need to provide vendor ID, product ID, revision to the host. Next, we have test unit ready callback. Using this, we need to tell the host whether the disk is ready or not. Next, we have start and stop callbacks. Using this, we need to handle eject load command sent from the host to the device. Next class we have storage geometry and capacity. In this we have capacity underscore callback functions, using which we need to tell the host the total number of blocks and block size currently present in our device. Then we have data transfer operations. We have read callback. This callback is invoked when host trying to read some data from the device, and likewise there is a write callback that is called from the host when host is trying to write some data to the device. Then we have extended custom commands handling, under which we have TUD, MSC, SCSI callback. It is where we catch all the unhandled or custom SCSI commands. Now let's see how we have to make changes in USB descriptor.c. First, we are defining total config length. This includes the default config plus the MSC descriptor config length, because we need to send both the config to the host. Next, we are defining our endpoints. Here 05 is out, is used for data going from the host to the Pico, and 85 that is in from the Pico to the host. Let's now define interface number to tell TinyUSB that we have just one interface, our mass storage class interface. If we had other features like USB CDC interface, we list them here too. Then we are defining the string descriptor indexes. Each string that describes our device has an index number. It's just a neat way to organize the text information for USB enumeration. And now the main part, the configuration descriptor. We add our MSC interface descriptor along with the default TUD config descriptor. Finally, let's look at the string descriptor. These are the names that show up under USB property on the computer. We just add our interface TinyUSB MSC to the end. The descriptor file just adds the USB identity layer so our Pico can be recognized as a mass storage class device by the host computer. Now we will integrate our previously implemented FAT12 file system with the Pico project. We just need to include the FAT12 code to a custom file named misc_disk.c, where the previously mentioned callbacks will be defined as well. MSC init will be called from the main function to initialize the virtual file system in the RAM. Now we'll be implementing the previously mentioned callback functions to handle disk operation with respect to our FAT12 file system. Firstly, under the device identification status callback, we will define inquiry callback function. This is to send our device vendor name, ID, version to the TinyUSB stack. Next, we will define test unit ready callback to handle the test unit ready command sent by the host to check if device is in usable state. If the device is not in usable state, we will use TUD set sense to tell the host that device is not ready. Finally, we define start and stop callback. This is invoked when host is trying to load or unload the media. Here, we are just caching the ejected state to stop our device functionality with respect to USB. Next, under the storage geometry and capacity, we will define capacity callback function. Host uses this function response to identify the storage capacity. Here we are sending the total block and block size currently present in our device. Then under the data transfer operation, we will define two callbacks. Read10 callback, which is invoked when host is trying to read data from the device at logical block address LBA of buffer size data length. We just jump to the location in our virtual file system and copy the data from that location to the destination buffer requested by the TinyUSB stack. Finally, we define write10 callback function, which is invoked when host is trying to write data to the device at LBA address. We just copy the data sent by the host to the respective location in our virtual file system. Finally, we will handle the extended custom command using the SCSI callback function. This function is invoked from the TinyUSB when it receives any command that is not handled by it. Here we are handling a particular command called prevent allow underscore medium removal that is sent by the host to direct devices not to disconnect while reading and writing. For the rest of the unknown commands, we are sending an invalid response via the TUD set sense. In both of the cases, we will be sending an empty response to the host. Now let's look at our main firmware file. Along with a LED blink pattern that shows up mount and unmount status, we will call MSC init inside our main function. That initializes our in-memory FAT12 disk when Pico boots up. So when we plug in the Pico to a host computer, it shows up a USB device. We can browse it, view files, and even verify the layout we have built earlier. Hi everyone, for demonstration I am using Ubuntu here. This is a virtual machine to which I have connected our Raspberry Pi Pico that you can see on the right hand side corner. Right now it is mounted to the device. You can see this is our tiny USB. Now what I'll do is I'll disconnect it. Now I will reconnect it. As you can see, initially is not mounted. Now it got mounted. And as you can see, you saw a tiny USB device getting enumerated here. So if you check for LSBLK, so this is our device. So if you do file, so our device is mounted on this location. First of all, let's check file on the STP. You can see the exact details that we have seen earlier. So this is DOS MBR, OEM ID is MS.5.0, FAT1, there is 5 root entities is 16, volume is less than 32 MB, sectors are 16, media descriptors 0 FAT and everything. Let's also try fstat. So yeah, so it's again file 2. So that's it. Let's quickly recap what we have learned in this video. We have explored how a mass storage class device works, how to integrate a FAT12 file system with TinyUSB, and how to implement the MSC callback functions for full USB read-write functionality. In the next part, we will continue to extend this project further, taking our Pico-based storage to the next level. As always, the complete resource is available on my GitHub repo. If you found this video helpful, don't forget to like, share and subscribe so you don't miss the next video. Thank you for watching and see you in the next one.